In the last class, we saw that we can represent different logic gates using single layer perceptron. But in case of XOR gate, so we cannot represent it properly. So we need to take help of the multi-layer perceptron. So today we will be talking about different facets and aspects of multi-layer perceptron, and we will see that the similar the XOR gate can be represented by this multi-layer perceptron when we increase the number of layers between input and output. Okay. Now, what are the limitations that we saw in single perceptron? So, perceptrons are considered to be monotonicity property. So, these perceptrons have a monotonicity property. That means if a link will have positive weight, then activation can only increase as the corresponding input value increases. That means if the corresponding input value for a particular link is increased, then the activation will also increase. Okay, so when the link will be found to be positive weight, then only the activation can increase when the input value is increased. Okay, so if we consider for a particular link, then the corresponding input value can be considered irrespective of the other input values. So accordingly, the activation function react or activation function computed. Perceptrons can represent functions where the input interactions can cancel one another's effect. Okay, so for example, we have considered XOR gate. So XOR gate cannot be represented by single layer perceptrons because for other gates and or not gate, we have seen that only one linear classifier can classify the examples into two different classes. But in case of XOR gate, so single classifier is not able to classify the examples into two different classes. So for that we need some other neural network, so which will be able to classify the examples into two different classes. So for example, today we will consider the multi-layer perceptron, and we will see that multi-layer perceptron is able to classify the examples properly when we represent the XOR gate using multi-layer perceptrons. Next, the perceptrons can represent only linearly separable functions. So that we saw in the last class that perceptrons only can represent linearly, or we can say the functions which are linearly separable can only be represented. Now, since we are interested to know the different aspects about the multi-layer perceptron, then what are the different features which are having with multi-layer perceptron, so that would help us to represent a complex function using multi-layer perceptrons. So firstly, the model of each neuron in the network includes a nonlinear activation functions, and in this case the nonlinear activation function is differentiable. Okay, so basically when the nonlinear activation function is used in the network, then that would be found to be a differentiable. Okay, so that is why we can represent any complex function using multi-layer perceptrons. So basically here we can map the induced input at the activation function into some nonlinear form, and where the functions in the nonlinear feature space can be found to be very easy to classify. Secondly, the network contains one or more layers that are hidden from both the input and output nodes. Okay, now why we call this is hidden layer? Because in the training examples we cannot see the hidden units. Okay, only we can see the input units and output units. and that is why it is said the hidden layer. Okay, so it is hidden from both input and output nodes. Thirdly, the network exhibits a high degree of connectivity, the extent of which is determined by synaptic weights of the network. Okay, so in multilayer perceptrons, we can see that uh, here the network shows the high degree of connectivity. High degree of connectivity means if we consider multilayer perceptron as a fully connected network, then we will see the neurons in the current layer. uh, each neuron in the current layer is connected to all the neurons in the previous layer. Okay, so that is why multilayer perceptron is can be a fully connected network, and it can show a high degree of connectivity. Okay, and this high degree of connectivity can be determined by synaptic weights or just weights of the network. So these weights are associated with the links, and which are to be combined with the corresponding inputs. Now here we can see the architecture of multilayer perceptron. So in this multilayer perceptron graph, here we can see that there are two hidden layers. Okay, one input layer is provided, and two hidden layers and one output layer. Okay, and here we can see that this is a fully connected multi-layer perceptron network. So here you can see that the first, if we consider the first hidden layer, in the first hidden layer, each neuron in the first hidden layer is found to be connected to all the inputs in the input layer. Okay, similarly, if we consider each neuron in the second hidden layer, then we can see that each neuron is found to be connected to all the neurons in the previous layer. That means the first hidden layer. Okay, so if we consider this type of multi-layer perceptron network, then we need to see that input layer feeds the uh, input signals, and it is propagated through the links, and it reaches to the first hidden layer, neurons of the first hidden layer. So here in the first hidden layer, the computations are done. So computations means the we summing up the input signals and weights. Okay, and then it is been transformed to another continuous values by activation function. Similarly, when the output is generated by the hidden units of the first hidden layer, then this output is uh, is, uh, fed to the hidden units in the second hidden layer. Okay, so the output of the first hidden layer will be acted as the input to the second hidden layer. Okay, and the outputs which are generated in the hidden units of the second hidden layer are to be transmitted to the output layer, neurons of the output layer. And here we we can also perform the computations as summing up all the inputs and the associated weight, and then we transform them to a output some output value, and based on that output value we can refer whether the examples are classified as some class X or not. Okay, so if we have a number of neurons in the output layer, that means the number of neurons will be equal to the number of classes. Now, if we consider the binary class, then only two neurons will be found in the output layer. If we consider n number of classes to be classified, then we have to consider n number of neurons in the output layer. Now, what are the signals we can observe? We can observe in multilayer perceptron networks. So, basically, we can consider two different signals. One is called the functional signals, another is called error signals. Now, what is functional signal? So if we consider this diagram, then we can see that the functional signals are propagated in the so here the forward, that means the in the forward direction the functional signals are propagated. But if we see the error signals are propagated backward direction. Okay, so the functional signal can be considered as an input signal, or we can other way we can say this is the stimulus, so that comes in at the input end of the network. That means this input signal or the functional signal is initiated at the input layer. Okay, and these functional signals are propagated through the network links in the forward direction. Okay, and finally it is been emerged as the output end of the network as output signal. So the input signals or the functional signals are propagated through the links of the multilayer perceptron network, and it has been emerged at the output layer, and output layer as an output signal. Now if we see the error signals, so this is the second kind of signals which is also propagated through the network. So here the error signal is originated at the output neuron of the output layer. Okay, and it has been propagated backward direction through the network. So basically here we are studying two different types of signals which are found in the multilayer perceptron network. Now, what are the different tasks of hidden and output neurons in MLP? So, if we consider hidden and output neurons in multilayer perceptron, then here the computation of the function signal is appeared at the output of each neuron. So when we compute the functional signal which is been appear at the output of each neuron, so it is been then expressed as a continuous nonlinear function of the input signal, and the synaptic weights are associated with the neuron. Okay, so here we basically here we compute compute the function uh, at the first hidden layer, or it may be in the other hidden layers in terms of the input signal and synaptic weights, so which are found to be associated with the neurons. Okay, and the second task of hidden and output neuron in MLP is the computation of an estimate of the gradient vector. Now, why we estimate the gradient vector? So this gradient basically represent the direction of move. So in which direction we will search the optimal values, so that can be represented by this gradient. Okay, so the gradient of the error surface with respect to the weights connected to the inputs of neuron. So the computation of an estimate of the gradient vector which is needed for the backward pass through the network. Okay, so when we need to update the weights, we need to first estimate the gradient vector or gradients. Okay, so that we can update the weight which is to be propagated to the propagated backward direction. That means if we calculate the error at the output neuron in the output layer, then we have to minimize that error function so that we can obtain the gradient vector. And when we obtain the gradient vector, then only we can update the weights, and that to be propagated to the previous layer. Okay, now here the hidden neurons will act as feature detectors. So if we see the diagram, then we can see that there are two hidden layers, first hidden layer and second hidden layer, which are observed between input layer and output layer. Now, whatever the number of hidden layers we use, the hidden neurons will act as the feature detectors. So So it is considered to be a lead a critical role in the operation of the multilayer perceptron. Okay. Now, as the learning process progresses across the multilayer perceptron through the network links, the hidden neurons will begin to gradually discover the salient features. And these salient features are characterized the training data. Okay. So, if we can consider any number of hidden layers in between input layer and output layer. Now if we consider the first hidden layer is fed by the input signals from the input neurons of the input neurons in the input layer. Okay. Now here the neurons in the first hidden layer uh, will try to discover the salient feature properties of the input signals or the input features. Okay. So across the hidden layer, across the a number of hidden layers, the we can discover different shapes or different salient features of the input signals, and we use this salient feature or input signal to characterize the training data. That means when we feed a training data in the input layer, so that is the raw data. Okay. So we do not know much about the input signals or the training data. So when it is been fed across the hidden layers, or it is been propagated across the different hidden layers, then only we can discover the different salient features of the input signals. Okay. And the hidden neurons perform a nonlinear transformation on the input data into a new space called the feature space. Okay. So when the activation function is fed with induced output of the aggregation function, then the nonlinear transformation is performed at the activation. Okay. So activation function is responsible to perform a nonlinear transformation on the input data into a new feature space, which is in which we can represent the uh, training data more wisely. Okay. So in this new space, or in this new feature space, the classes of interest in pattern classification tasks so may be found more easily separated from each other. Okay. Now in this regard, we need to know how the learning is performed. Okay. So if we consider the learning in multilayer perceptron, then we can have two different learning algorithms. The first one is called the batch learning strategy, another is called the online learning strategy. Now let us consider a multi-layer perceptron with an input layer of source node, one or more hidden layers, and an output layer consisting of one or more neurons. Okay. So here we are considering one input layer, okay, one or more hidden layers, and one output layer. Now we can feed the network with the training examples, n number of training examples, in which here you can see that here xn represent the input signal, and dn represent the desired output or target output. Okay. So we have n number of such examples. Now we will perform the learning using this n number of examples. Okay. And this each of these signals will be fed to the hidden layer through the input neurons in the input layer, and we can perform the summation and activation functions in each neurons in the hidden layer as well as in output layer. Okay. Now let us also consider that here yjn denotes the function signal which is produced at the output of neuron j. Okay. output of neuron J in the output layer. Okay, so if we consider there is a neuron J in the output layer, then here Yjn will denote the function signal which is produced at the output of neuron J in the output layer by this input signal Xn, which is applied to the input layer. That means this Xn is applied to the input layer. Okay, and here Yjn denotes the functional signal which is produced at the output of neuron J in the output layer. Then the signal, error signal, which is produced at the output of neuron J can be defined by this equation. So this is the error function. So for a single neuron, we can define the error signal or error function as Ejn equals to Djn minus Yjn. Okay, Ejn, so here Djn is the desired output of the target output and Yjn is the observed output. Okay, observed output of the actual output. So we take the deviations between these two and we get the error for a single neuron in the output layer. Now here, as I said, that Djn is the, sorry, it is jth element would be. So Djn here is the jth element of the desired response vector Dn. Okay, then we can compute the instantaneous energy of neuron J, which is defined by this function fjn equals to half of e to the power e squared jn. So this is nothing but the, we are taking the square of this error. We are taking the square of this error. Okay, so when this square of this error represent the residuals. Okay, so residuals at the neuron J. Now we will summing up the error energy contributions of all the neurons in the output layer. Now, instead of considering just one neuron, we can consider all the neurons in the output layer, and for that we can express the total instantaneous error energy of the whole network as f of n equals to summation over f of fjn. Okay, so here j belongs to c. What is c? C is the total number of neurons in the output layer. Okay, and as we have already computed the error for each neuron in the output layer, so therefore, so this this is been considered as the residuals at each neuron in the output layer. Okay, and in place of fjn we can write ej square n. So this summation is computed over the ej square n, and where j belongs to c. So for the total number of neurons in the output layer, we can compute this instantaneous error energy. This is called the instantaneous error energy, this function. So f of n, this is the instantaneous error energy. Now, now with these training samples consisting of n examples, the error energy can be averaged over the training sample or the empirical rigs. Now this average error energy can be averaged over this n number of training examples. So which is done in this equation. So here we can get the average of energy functions, that is f of this ab represent the average. Okay, so this average function is defined by 1 by n summation over this f of n. So we have already computed the f of n. Okay, now we need to get the summation over this f of n, and f of n is defined by this summation over ej square n, where j belongs to c. So we can further rewrite this function as 1 divided by 2n summation over this double summation is used over this ej square n. Okay, so here C represent the total number of neurons in the output layer. Okay, and here capital N represent the total number of training examples which are used for training the network. Okay, now depending upon the supervised learning which is performed at, in multilayer perceptron, we can identify two different methods. Okay, so as I said that we can have two different methods. One is called the batch learning, another is called online learning. Now what is batch learning? So in batch learning method, we can adjust the synaptic weights of the multilayer perceptrons. Okay, and which is multilayer perceptron, and which are performed after presenting all the n number of training examples in the to the network. Okay, so basically here we are trying to adjust the synaptic weights by presenting all the n number of training examples to the network. And when we perform this when we perform this weight adjustment, basically we constitute one epoch of the training. Okay, so until and unless we get the first output, we cannot compute the error function, and when we cannot compute the error function, we cannot optimize that function to get the gradient. Okay, and when we cannot get the gradient, we cannot update the weight. Okay, so the when the input signals will be uh, propagated in the forward direction for the first time to generate the output, so we basically constitute one epoch of the training. Okay, so here the cost function for batch learning will be defined by the average error energy. So here the cost function for batch learning will be defined by the average error energy. This is a for FAV. Okay, so this represent the average error energy, and the adjustment to the synaptic weights of the multilayer perceptron will be made on an epoch by epoch basis. Okay, so this is the criteria to be a batch learning strategy that we can found in the multilayer perceptron neural network. Okay, so here the learning is done by epoch basis, by which we can adjust the synaptic weights in different layers by propagating the updated weight to the previous layers. Okay, the next is online learning. So in online learning method of supervised learning, we can adjust the synaptic weights of the multilayer uh, perceptron by example basis. So what is the example by example basis? Now, as I said that we are having n number of training examples. Now if we provide the first training example, or if we feed the first training examples to the input layer, then input layer will propagate or transmit that input signals to the first hidden layer. Then after generating the outputs in the first hidden layer, then that will be transmitted again to the second hidden layer. So in this way, when the outputs of the last hidden layer will be found as uh, input to the neurons of the output layer, then we can get the first output. And when the first on the output for the first time will be generated, then we can compute the error. Okay, and accordingly we will get the gradient. Then we will update the weight, and that will be propagated backward across all the previous hidden layers. Okay, so this is for the one example. So first we feed the one example, first training example, then second training example, then third training example. In this way we can continue until the last training examples are fed to the input layer. Okay, now if we consider this online learning strategy, then this procedure works against the parallelization of the online learning. Okay, so this is the procedure which works against the parallelization of online learning. Now we will talk about the backpropagation algorithm. So we need to when we perform the training and learning in the multilayer perceptron. So this is one of the uh, important aspects in multilayer perceptron. So this important aspect is known as the backpropagation algorithm. So if we consider this network, then here we can see that here we are feeding the input signals to the input layer, all the neurons in the input layer. So this is the bias, y0 equals to +1 is the bias, and this set of input signals are the input vector. This input vector is fed to the neurons of the input layer, and then these input signals are propagated through this link to the first to the neurons of the first hidden layer, and this is the weight wj0n equals to. So here we can consider this wj0n is considered to be the bias bjn. Okay, and rest of the weights are found to be associated with the input links to the uh, hidden units in the hidden layer. Okay, and here vjn is considered as the induced input at the activation. So this is the activation function. This is the activation function, and this input at the activation function is nothing but the summation of input signal and weights. Okay, so that is why this vjn is called the induced input at the activation function. And when this induced input is provided to the activation function, so activation function performs the nonlinear transformation of the induced. Okay, and then it is been generated as yjn, which is also which is called the output of the activation function. Okay, and here we compute the error by comparing with the desired output or target output. So this is the actual output yjn, and this is been compared with the desired output. Now we get the deviation, and this deviation nothing but the error ejn. Okay, so for each neuron j we can compute this error ejn after having the output yjn to be compared with desired output djn. Now, neuron J is being fed by a set of functional signals which are produced by a layer of neurons to its left. To its left means it is being produced at the input layer. Okay. The induced local field VJN is produced at the input of the activation function associated with neuron J. So this induced input at the activation function can be defined as the summation over wjin. This wjin is the weight which is found associated with each input link towards the hidden units in the hidden layer, and here yin is the yin is each input signal. Okay, so if we have m number of signals, then we can compute this induced input at the activation function by summing up the weights and input signals. Okay, so this is the linear combination of these two components. So here m is the total number of input signals which are applied to neuron j. Now the synaptic weight Wj, as I said that this Wj0 is found to be equal to the bias j. So which is actually y0 equals to +1. So this y0 equals to +1 is considered to be denoted by this Wj0, where Wj0 can also be found to be equal to this bias bj. Okay. Now the function signals yjn which is appeared at the output of neuron j, is iterated and so neuron j at iteration n. So if we consider that n is the iteration, then this functional signal yjn which is appeared at the output of neuron j is found to be yjn equals to this is the phi j vjn. Okay, so in terms of induced input, we can compute this we can compute the nonlinear transformation by applying this phi j activation function. Okay, and this will give us the output functional signal yjn. Now similar to least mean square algorithm, the backpropagation algorithm will apply a correction. This is the correction delta wjin to the synaptic weight wjn. Okay, so this correction will be applied. So basically this is important to obtain for updating the initial weights or the weights in the previous layer. Okay, now this found to be proportional to the partial derivative del f of n divided by del wjin. So with respect to weight, we can compute the derivative of the function f of n. Okay, and this will give us the gradients. Now according to the chain rule of calculus, we can express the gradient as del f of n divided by del wjin, and this will be found to be equal to del f of n by del ejn. Okay, so here we can see that this term is found over here. Okay, so del ejn by del yjn, again this term will be found over here. Okay, so del yjn divided by del vjn, and again this term will be found over here, del vjn divided by del wjin. Okay, so that is why this is called the chain rule. By using chain rule, we can obtain this gradient. This is the gradient, and this derivative is obtained with respect to the weight. Now this partial derivative will represent the sensitivity factor. Okay, and this sensitivity factor can be determined. This sensitivity factor will determine the direction of search in the weight space for the synaptic weight wji. Okay, now so direction of search in weight space means here we are trying to reach the optimal value. So optimal value so that we can minimize the error. Okay, so in the direction of finding the optimal value, so we can obtain this partial derivative. Okay, and this partial derivative will represent that sensitivity factor, and the sensitivity factor will determine the direction of search in the weight space. Now already we have computed this function f of n, and if we take the derivative with respect to error for each neuron j, then we will get this ej of n. Okay, this ej of n. So this derivative will give the error at neuron j. Okay, and we have already computed this error for each neuron. Okay, so if we take the derivative of this function ejn with respect to yjn, then we will get -1. Okay, again if we take the derivative of yjn with respect to induced input at neuron j vjn, then this will give us this phi dash j of vjn. Okay, so here vjn is the induced input at the activation function, and this is the and this phi dash j is nothing but the activation function. Okay, and again if we consider the induced input for neuron j, then this can be so we can obtain the derivative of this function with respect to weight, and this will give us yin. So this yin is nothing but the input which is fed to the input layer. Okay, and when we combine all these all the result of all these derivatives, then we can obtain the derivative of function f of n with respect to wjin. Okay, so this function is nothing but, this f of n is nothing but the error function which is computed for neuron j with respect to weight wjin. So this ji means what? Ji means the link from input I to output neuron j. So input neuron I to output neuron j. Okay, so this can be this may be found between input layer and hidden layer, between hidden layer and output layer. So we can consider these links, and which can be represented by this two indices ji. Okay, so when we combine the result of all these derivatives, then we will get the function the derivative of the function f of n with respect to weight. Now these corrections that we obtained for updating the initial weights, or the weights in the previous layers, now these corrections can be applied to wjin. Okay, so if we consider this is the weight, initial weight, or the weight at the previous layer, then this can be updated, or this can be modified by defining the delta rule. Now what is delta rule? Now delta rule says that we can obtain this delta wji of n by having this minus eta delta f of n by delta wjin. Okay, so this is the partial derivative with respect to weight, which is multiplied with this eta. This eta is nothing but the learning rate. Learning rate means this learning rate parameter, describes what will be the step size, towards the optimal value. Okay, or towards the convergence. So whenever we will get the optimal value, then at that optimal value, the gradient will be found to be 0, and we will say the function is converge to this optimal value. Okay, so this eta is known as the learning rate parameter, and this learning rate parameter, so either we can take small learning rate, we can take small value for this learning rate parameter, or we can take a large value for a learning rate parameter. That means if we consider small values for eta, then the learning becomes slow. If we consider the large values for this learning rate eta, then learning becomes very fast. Okay, but we have to keep balance between these two extremes, so that we can consider the wise value for eta, so that learning can be done such a way that we can minimize the error function. Okay, or minimize the error for each neuron in the output layer, or the output layer, and we can get the minimum deviations between desired output and actual output. Now here you can see that here we use the minus sign, or we obtain the minus sign. So this minus sign is considered for gradient descent in weight space. Okay, and here we seek a direction for weight change that reduces the value of function f of n. Okay, so that is why we consider this or we obtain this minus sign in this delta rule, which is defined for updating the weight. Okay, so therefore we can write this delta wji of n equals to eta del jn yin. What is del jn? Can you tell me what is del jn? Eta is the learning rate, del jn, and here we obtain the del jn, which is multiplied by the input yin. So here the local gradient is defined by this del jn. Okay, so here the local gradient is defined by del jn, and which is given by this derivation. So finally, when we took these derivations, so we can reach this final combinations of error at neuron j and activation. So this is the activation phi dash j, which is defined over this induced input. Okay, so these local gradients will point to required changes in synaptic weights, and according to this above derivations, the local gradient del in for output neuron j is equal to the product of the corresponding signal ejn. Okay, this is the corresponding error signal for ejn for that neuron, and derivative and this derivative of the associated activation functions. So this derivative will represent the function which can be associated with the activation or nonlinear transform. Now we can summarize the relations that we have already derived for the backpropagation algorithm. So firstly, here the corrections delta wjin applied to the synaptic weight, which is found connecting neuron I to neuron j, and this can be defined by this delta rule. So the backpropagation algorithm can be defined by this delta rule, which is nothing but the weight correction, which is given by the learning rate parameter multiplied by local gradient multiplied by input signal of neuron j. Okay, so this is the summarization of the backpropagation algorithm in multilayer perceptron. So firstly, we corrected the weight. Okay, corrected the weight, or we have applied this delta wji of n to the synaptic weights. Okay, and secondly, the local gradient del in depends on whether neuron j is an output node or a hidden node. Okay, now if the neuron j is found to be output node, then this del I of n will be found to be equal to the product of the derivative this phi dash j vj of n and the error signal ej of n. So both these terms del I of n, okay, and ej of n, both these terms will be found to be associated with neuron j. Now if the neuron j is a hidden node, okay, so firstly we consider j is output node. Okay, now we are considering j is hidden node. Now for this hidden node, the delta in will be found to be equal to the product of the associated derivative phi dash j of vj of n, and the weighted sum of del s will be computed for the neurons in the next hidden layer or the output layer. So that are been connected to neuron j. Okay, so j may be the neuron in the output layer, and j may be the neuron in the hidden layer. So for both considerations, so we can obtain this del I n, okay, and this ejn, and then we can associate, or we can combine these two terms after considering the learning rate parameter in the backpropagation algorithm. So similarly for the hidden net, we can obtain this, we can obtain or we can derive the backpropagation algorithm in terms of this learning rate eta, local gradient del j of n, and input signals. Now, in the application of backpropagation algorithm, two different passes of computations are distinguished. The first pass is referred to as the forward pass, and the second is referred to as the backward pass. Now, what is the forward pass? So, in forward pass, the synaptic weights remain unaltered throughout the network. Okay, and the function signals of the network which are found computed on a neuron by neuron basis. Okay, but in case of backward pass, on the other hand, we'll start at the output layer by passing the error signals to the previous layer. Okay, now layer by layer we can consider these error signals to be passing through the network in backward direction. Okay, and we can recursively we can compute the delta. This is the local gradient for each neuron, and this recursive process will permit the synaptic weights of the network to undergo different changes in accordance with the delta rule. Okay, now considering the delta rule, we can compute the local gradient recursively for each neuron, and this process will permit us the synaptic weights of the network to be modified in accordance with the delta rule. Okay. If you have any questions, you can ask me. Otherwise, we will stop now. Any questions? Okay.